Och med oss har vi Arya Manjal som är doktorand i matematik vid KTH. And with that said, I think I will leave the word to you.
Thanks a lot, Eileen. Thanks a lot for the invitation. Thanks a lot for having me today. All right, let's start with something fairly simple. The actress Jamie Lee Curtis won an Oscar yesterday, right? How many of you have seen Freaky Friday? Some of you? Anybody? You roughly remember the plot, right? In Freaky Friday, Lindsay Lohan exchanges minds with the Jamie Lee Curtis mother, and they get trapped in this, in this situation in which Lindsay Lohan is in Jamie Lee Curtis's body and Jamie Lee Curtis is in Lindsay Lohan's body. And hijinks ensues and sort of crazy things happen. And that's essentially the same situation that I want you to keep in mind, this idea of people having their minds swapped. And that's the only situation, it's sort of the only thought experiment that I want to do with you today. And we're going to do a bit of a demonstration, and I'm going to describe a scenario in which a group of people have their minds swapped, and then we want to sort of use a mathematical result, use something foundational about the way that numbers are swapped and numbers are arranged in order to get back to the conclusion, or get back to like everybody being in their correct, every mind being in their correct body. So this is what happens. We have a machine. The machine can swap the minds of two people, but once a particular swap has been done, it cannot be undone. So let's take you two guys in the front. What are your names?
Justice.
Justice and?
Monza.
And what, sorry?
Monza.
Okay, right. So suppose the two of you, sit down in this pair of chairs, and you have not right now. I'll call you up at some point. But suppose you do, and your minds are swapped. Then, in order to undo that, we can't directly use the two of you again on this machine. We're going to have to use like a third person, and then swap with that person, and then use that person to swap with you. Now, that's the only limitation of this machine. That once a swap has been done for a pair of people, it can't be undone using the machine. The same pair can't be undone. Now, several such switches have occurred in a group of people. We have some group of people, maybe there are just 5 of them. For the purpose of the demonstration, it's going to be 5. You can imagine any large number. And within this group of, say, n people, lots of people switch, but with the condition that they don't unswitch, right? And at each time they switch, one person's mind gets sent to somebody else's body, and somebody else's mind gets sent to the person's body. All right? So lots of such switches have occurred, just like in this picture out here. We've got 2 people, their minds are being swapped. For some reason, it's an alien and a boy. But the question that we want to ask, and the question that sort of where this situation arises from, is that can we use the machine to send each person's mind back to their correct body with this limitation that I can't undo a particular swap that I've done? So if I want the two of you to get unswapped, not right now, but, I'm going to have to use somebody else. And the question is, can this always be done, no matter how large a group of people you begin with? So suppose I have 1,000 people and I do crazy, several swaps among these people. Is it always possible for me to undo that and arrive back in the correct situation, in which everybody's mind is back in their correct body? All right, that's the question I'm asking today. And I'll spoil the answer for you because it's a good answer. And the answer is yes, you can, using a little maths. That's the short answer, all right? But the slightly longer answer is that you actually can't do it using just the same group of people. So if you had, say, 1,000 people and this happened and the situation happened, then in order to use the same machine to right this wrong and send everybody's mind back to their correct body, you actually have to use 2 extra people. And these 2 extra people, you sort of take turns swapping with them, and somehow you're going to end up in the situation in which everybody's mind is back in their correct body. So in a bit, we're going to do a bit of a demonstration. We're going to call 5 of you up, and Eileen and I are going to be the 2 helper people who sort of right this situation of being wrong. Now, all of this is this hypothetical thought experiment, this experiment that involves a machine. So the question is, how do we explain this? How do we sort of model this, using maths? And the answer to that is using something called permutations. Now, you might have seen permutations before. You might have studied permutations and combinations in this grade or the grade below, or maybe even before that. And that's what we'll be talking about for the next few minutes. Right. So before I continue, I should say that this plot line isn't my creation. It's definitely, it's well known. And in particular, it's a plot line from this TV show called Futurama. I don't know. Have any of you watched that? Yeah? Okay, so then maybe you know that Futurama is like Simpsons, is sort of like this math crazy show which loves, shoehorning math theorems and math results into these plot lines. It has, I think it has the same creators. I mean, at least it has the same aesthetic. It's sci-fi, it's crazy, it's weird, it's kooky, and in one such result, in one such episode, you have this situation of a group of people having their minds swapped, and then trying to, and the point of the episode was to write this and send everybody's mind back to their correct body. All right, but now the goal for us today is to rephrase this in terms of permutations. Now, a permutation, you can define that as a function from a finite set to itself that is both injective and surjective, but those words are boring, right? We're not going to get into all of that. In a different sense, and in a sense that you might have already heard of, is that a permutation is a way, suppose it's a permutation on the set 1, 2, 3, all the way up to n, then a permutation is just a way of writing down the numbers 1 to n next to each other in any order. So like I've said on the board, an example of a permutation is this thing 5, 4, 3, 2, 1. Because I've taken the numbers from 1 to 5 and I write them down in any order. I can also write 5, 1, 2, 3, 4, or I can also write 5, I don't have to begin with 5, I can begin with anything, and write something like this. So if you have seen a bit of this before, you will know that there are 120 possible ways for me to write, write these numbers down in any such order. But we're not going to get into the counting aspect of it as much as representing these things. Now, I want you to think of this in two ways. One way is this thing that I've already explained. The permutation written as one line, yeah? Permutation in one line notation, as they say. And that's one way of doing it. And maybe out here it's not immediately clear what this means, but this is like saying the first position is occupied by 5, the second position is occupied by 4, the third position is occupied by 3, the fourth position is occupied by 2, and the fifth position is occupied by 1. Now, we might want like a better way of representing that, a way in which you sort of understand the relationships between the individual numbers and maybe group the numbers that are in like a path by themselves or a trajectory by themselves. All right? So take the first picture out there, picture A. So over there, the permutation is depicted as a function, which is probably the first way you're taught about these things, which is, 1 goes to 5, so the arrow from 1 to 5. 2 goes to 4, so arrow 2 to 4. 3 goes to 3, 4 goes to 1, and 5 goes to 2, which is also analogous to this. But suppose I ask myself, is there a way I can begin by writing down the number 1 and then finding all the elements in that sequence where 1 goes to something, that something goes to a third something, and is there a way that after that I come back to 1? And well, there is. In this case, I start at 1, 1 goes to 5, and then if I ask what happens to 5, well, 5 goes back to 1. So 1 and 5 are in a little cycle by themselves. So that's why in the second picture, I've sort of taken this permutation 5, 4, 3, 2, 1 and decomposed it into cycles. So 1 and 5 are together in a group because they are swapping with each other. 2 and 4 are together in a group, and 3 goes to itself. So we say 3 is in a cycle by itself. And as you can see, these cycles don't interact with each other, right? There's no interaction. There are no arrows from here to here or here to here or between them. So that's why we say that these cycles are disjoint, right? There's no intersection between them. So if I wanted to express the permutation 5, 4, 3, 2, 1 as a product of disjoint cycles, which is the main thing that we want to do mathematically today, one of the main things, then what we have to do is ask ourselves, well, 1 goes to 5 and 5 goes back to 1. That's what this bracket notation means. Similarly, 2 goes to 4 and 4 goes to 2, and 3 goes to itself, which is just 3. Now that's cycle notation, and really that's the language we're going to be using to express more of the results in permutations, but also to model the situation from the Futurama episode, which is to express the situation of mind swaps as a single permutation. All right? Yes, so let's talk about the same permutation sigma. So the sigma, as we had written it, it had 3 cycles, right? It had 1, 5, 2, 4, and 3. And you might wonder, is it okay? Are there rules to writing these things down? So what if I had swapped 2 and 4 and made it 4, 2? Well, that's also acceptable because you've preserved the cyclic order, right? This still says that 2 goes to 4 and 4 goes to 2, so we're fine, all right? So order the cycle in any which way you want, which is, I should have said that first, which is also a way of saying I can write 2, 4 out here, then I can write 3, and then I can write 1, 5. And all of this just stems from the idea that these cycles are disjoint, so I can move them around and I'm fine. And they represent the same thing. They represent the same way of writing this. Yeah? That's the main idea out here. So like I said out here, 1, 5 is the same as 5, 1. 2, 4 is the same as 4, 2, and so on. And in this situation, this cycle, it has 3 cycles, 2 of length 2 and 1 of length 3, 1 of length 1, sorry, which is 3 in a cycle by itself. Now, cycles can be longer, and permutations, the main idea is to sort of combine permutations, combine 2 permutations to give us a third one. So just as there's a notion of multiplying 2 numbers, 5 times 7 is 35, there's a notion of multiplying 2 permutations to give another permutation. And hopefully it should be clear to you that, it'll be clear in a few minutes as to what the rules are that govern this multiplication, this way of combining them. Right, so I said that this is sigma in one-line notation. So the two-line notation of it is just writing the numbers 1, 2, 3, 4, 5, and then writing the one-line notation below that, which basically tells you that 1 goes to 5, 2 goes to 4, 3 goes to 3, 4 goes to 2, and 5 goes to 1. So that's my first permutation. Suppose I had another permutation called tau, and tau tells us that 1 goes to 3, 2 goes to 1, 3 goes to 2, 4 goes to 5, and 5 goes to 4. Then the way to combine these 2 permutations is to begin with tau. Suppose in this order, sigma times tau. I could have used any sort of symbol out here, but I wanted to use this so that it doesn't look like it's normal multiplication. So if I begin with the 1 in tau, and I say, where does 1 go? 1 goes to 3. And then I ask myself, what happens to the 3 in sigma? 3 goes to 3. So 1 goes to 3, 3 goes to 3, so 1 goes to 3 out here. All right? Similarly with 2. Well, 2 goes to 1, 1 goes to 5, so 2 goes to 5. So at each number, I'm going to look at tau and see where does tau send that number. And suppose it sends that number to some number. I look at that same number in the first line of the 2-line notation of sigma, and then I see where that goes, and then I put that number in the slot for sigma composed with tau. So 4 in tau, where does 4 go to? 4 goes to 5. And where does 5 go to in sigma? Justice. In sigma, where is 5 going to? 1. So then 4 goes to 1 in the composed thing. That's the rule. All right? And similarly with the number 5, 5 goes to 4 and 4 goes to 2, so 5 goes to 2 in the composed permutation. Now, as you can see, it might be a little difficult to check each time. You have to draw this 2-line thing. It might be difficult to sort of see what exactly is happening. So the way to simplify this is to multiply them as cycles. All right, is to first take the permutation, convert it to cycle notation, and then multiply them as cycles. So we're going to get to the demonstration in a second, but I just want you to sort of understand how this situation of mind swaps is modeled as a permutation. So in this particular sense, what does sigma look like as a cycle? Well, sigma as a cycle, like we already know that. We just tied them up, or we just began at 1, and we tried to find a sequence where the last number maps back to 1, and then we just continue doing that for each number. So similarly with tau, well, we know that in tau 1 goes to 3, then we follow what happens to 3, 3 goes to 2, then we ask what happens to 2, 2 goes to 1. So 1 goes to 3 goes to 2, so I'm going to put them in a cycle by themselves. And similarly from the 2-line notation, you can also see that 4 goes to 5 and 5 goes to 4, so 4 and 5 are in a cycle by themselves. Now I want to combine this. I want to multiply these only as cycles. So I have as cycles, I want to multiply sigma and tau and get the cycle notation or the cycle representation of sigma composed with tau, sigma times tau, whatever you want to call it. So those question marks means I don't know yet. So we're going to figure this out together, all right? So Yes. So there's only one rule for multiplying cycles. So what we have to do is to begin with any element in the rightmost cycle. So I've written sigma composed with tau. Tau is in blue, sigma is in red, and the rightmost cycle consists of the numbers 4, 5. So begin with any number there. So you can name any number in the cycle 4, 5. You can choose either 4 or 5.
4.
4. So that where does 4 get mapped to according to the last cycle? You know it.
No.
Because 4 and 5 are a cycle by themselves. This just means that when I write these numbers like this, I just mean that 4 goes to 5 and 5 goes to 4. So the answer was just that 4 goes to 5 because they're next to each other.
Yeah.
So when I write 1, 3, 2, and the question is what does 1 map to, it just means whatever's in front of it, whatever number is right in front of it. And similarly, what happens to 2? What happens to 2 is whatever number is at the front of it, but cyclically. So 2 gets mapped all the way back to 1. Right. So that's just it. So the answer is that what happens to 4? 4 gets mapped to 5. Now think about the number 5 and look for the first occurrence of 5 to the left of the cycle 4, 5. Where is that? It's not in 1, 3, 2. It's not in 3. It's not in 2, 4. But it's in 5. So that tells us that 4 maps to 1. Because 4 maps to 5 and you look for the next occurrence of 5. 5 maps to 1. So 4 maps to that thing out there. And okay, I seem to have gone ahead. But then I take that number which I ended with, which is 1. And I look for where 1 maps to in tau. So I know 1 maps to 3. That's just in the first, in the second last cycle, the first cycle in blue. 1 maps to 3. And then I look for the next occurrence of 3 to the left of that cycle. And that is in a cycle by itself, which says that 3 maps to 3. And then there are no further occurrences to the left of that, which means that 3, that 1 maps to 3 because I was beginning with 1. So I continue and I get that, 3 maps to 2 out here. 3 goes to 2, and then I look for what 2 goes to. 2 goes to 4. So 3 goes back to 4, so I close this cycle. So like that, I'm able to represent these permutations, the product of two permutations, as a single permutation in cycle notation. So again, the reason that 2 goes to 5 is that 2 goes to 1 in the blue permutation, and then I look for what 1 goes to in the red permutation, and then 1 goes to 5. So 2 goes to 5. And 5 goes to 4 in the blue, and in the red, 4 goes to 2, so 5 goes to 2. Okay, so if that was a lot of numbers and a lot of brackets, I'm with you there. And the idea is to sort of gain facility with, multiplying these things together. So I promise you, this is going to be the last example, and then we'll get to the more interesting stuff. So we have 1, 2, 3, 4, 5, 6. We have 6 of these cycle things. And I want you to think of each of them as a permutation. The first permutation switches the numbers 1 and 2. The second permutation switches the numbers 1 and 3, and so on and so on. The last permutation switches the numbers 3 and 4. So in order to sort of multiply these things together, and we're going to be doing a bunch of that when we C2 all down, is to sort of figure out how to take these 6 permutations and represent them as sort of simply as possible. All right? So I'll do this with you. So let's look at 3. 3 is the first thing, is the first number in the last cycle. 3 goes to 4. So the next occurrence of 4 is here. 4 goes to 1. Now I'm going to look for the next occurrence of 1. 1 goes to 3. So and there's no further occurrence of 3 to the left. So 3 must go to 3. Similarly, if I start with 4, 4 goes to 3, 3 goes to 2, 2 goes to 4, so 4 goes to 4. Is that part clear? Is there something that's not coming through? So now suppose, okay, let's do this with somebody else. And it's totally cool if you don't know the answer. We can just work it out together. Let's start with 2. Who wants to take 2? Who wants to try and figure out where 2 goes to? Anybody? Yeah, 2. What happens to 2?
2 goes to 3.
Yes, and then to the left?
The next occurrence of 3 is in 1 and 3.
Yes, so 3 goes to?
1.
And then?
1 goes to 2.
1 goes to 2. So then, there's no more to do, right?
No.
So 2 goes to 2. Exactly. Thanks, Justice. Exactly. That's exactly what happened. And similarly, you play the same game with 1. 1 goes to 4. Then you look what happens next. Well, 4 goes to 2. Then is there a 2 to the left of that? There is. In the first cycle, and 2 goes to 1. So 1 goes to 1. And that is and that is sort of the idea out here. And of course, like I told you in the beginning, we can reorder these permutations. So this 3, 4, 2, 1 is the same as 1, 2, 3, 4. And this is a super important permutation. Right? This is a really important permutation. Oh, I don't know why there are 2 exclamation marks. There should be just 1 out there. But the idea is that that this permutation is the goal permutation that we want to get to. We have, yes, sorry, a question in the back.
What's a permutation?
Say again?
What's a permutation?
What's a permutation? Fair question, yes. So like I was saying in the beginning, a permutation is a way of writing down numbers in a sequence, one after the other, in order so that all of them are represented. So permutation on the set 1, 2, 3, 4, 5 is a way of writing the numbers 1, 2, 3, 4, 5. So take the numbers 1, 2, 3, 4, 5 and say them in any order. Say them now in any order.
1, 2, 3, 4, 5.
Yeah, okay, that's a really simple one, but say another one.
2, 3, 4, 5.
No, you can't do 6 because we're only limiting ourselves to 5. So 2, 3, 4, 5, 1, that's also 1, right? Because so you just name them in any order, that's a permutation. And now out here we're just talking about representing them in different modes. So this permutation that we named 5, 4, 3, 2, 1 can also be written as this. All right? Because essentially, yeah, I explained this at the beginning, but 1 and 5 map to each other, 2 and 4 map to each other, and 3 is by itself. All right? So yes, like I was saying, so this is the goal permutation, something where 1 is in a cycle by itself, 2 is in a cycle by itself, and so on and so on. The last number is in a cycle by itself. So we want to ask ourselves, or the goal really is to start at any permutation and reach this permutation using only swaps. And by swap, I just mean this a permutation which consisting of just 1, 2 cycle. Like 3, 4, that's a swap. 3, 2, that's another swap. But 2, 3, 4, that's a 3 cycle. So by swap, I just mean literally the something that looks like brackets with 2 numbers in it. All right? Okay, let's go back to the thought experiment. And let's talk about representing these mind swaps as permutations. So let's go back to exactly what happened. So we had a group of people. This group of people, they sat in these 2 chairs. Their minds got swapped. Then 2 more people sat. Their minds got swapped. And so on and so on and so on. So let's suppose we have 5 people. And we label them 1, 2, 3, 4, 5. We're giving them the names 1, 2, 3, 4, 5. All right? So I'm going to use this notation ij, this I double arrow j, to mean person I swaps their minds with person j. So suppose in the first instance 1 swaps with 3. And then in the next instance 1 swaps with 4. So after the second swap, after the first swap, 3's mind is in 1's body and 1's mind is in 3's body. But after the second swap, 1 now switches the third, like 1 had 3's mind in it, right? So now, after the second swap, do you agree that 4 has 3's mind in it? Right? Because we did these 2 swaps together. So like that, we execute, like say, 2 swaps with 5, 4 swaps with 5, and 3 swaps with 4. What you can see in this list is there's no repetition, in the sense that I didn't include, say, this thing swapping again, or this swapping again, because we can't. That's the rule. That's the rule of the machine. And you're not allowed to do that. So suppose that only these 5 swaps occur. Okay, these 5 swaps occur, and we want to represent that using permutations. So just to remind you, yes, 1 swaps with 3, 1 swaps with 4, 2 swaps with 5, 4 swaps with 5, and then 3 swaps with 4. Now, it doesn't actually matter what these things are, because once we represent them, we're going to represent each swap i's with j with the permutation ij. So this permutation ij is, you have to imagine that every other thing stays the same in this permutation. 1 goes to 1, 2 goes to 2, and so on, all the way up to I minus 1 goes to I minus 1. But when you reach the letter I gets, the number I gets mapped to j, and j gets mapped to I. And then after that, all the other numbers are the same. All the other numbers are mapped to each other. So you have these 5 swaps gives us these 5 permutations. And now each swap corresponds to a permutation, and each sequence of mind swaps corresponds to the permutation that is the product of these permutations corresponding to the mind swaps. So the situation that you get after executing all the swaps out here is the product of 3, 4 times 1, 4, 3, 4 times 4, 5 times 2, 5 times 1, 4 times 1, 3. Why is 1, 3 right at the end? Because we did 1, 3 first, right? And if you remember our notation of multiplying two permutations, if we did sigma times tau, that means that's the rule that says do tau first, then do sigma, right? That's the idea, that you essentially start with the innermost thing, start with the rightmost thing. So suppose we were to multiply these guys together out here. I've given away the answer, but you follow the same rule, right? What happens with the first number? What happens to 3 in the? We start with 3 in the rightmost cycle. 3 maps to 1, then follow what happens to 1. 1 maps to 4, then follow what happens to 4. 4 maps to 5. So 3 maps to 5. So 5 comes after 3 in this notation out here. Similarly, if we start with 1, 1 maps to 3. Then what happens to 3? 3 maps to 4, so 1 maps to 4. So like that, we represent this sequence of mind swaps, this situation of people swapping minds, as a single permutation. And that's essentially the takeaway of this talk. Have all of you understood that? Okay. Okay. So that's essentially what's going to happen. So we've had mind swaps occur, and at the end of the mind swaps, we say that corresponds to a single permutation of the numbers that we began with, right? 1, 2, 3, 4, 5. And again, the question that we want to ask is, can we use the machine to send each person's mind back to their correct body, which is the same as asking, can we sort of take this permutation and return this permutation to the goal permutation, which was using only swaps of a particular kind. All right. Now, at this point, we're going to call some of you up here and actually execute a little of these mind swaps. It's going to be a little corny. We're going to use this machine. We're going to plug this machine in. It's actually a plasma machine, plasma, right? And this will light up and all that. And we're going to execute that. And we're going to execute a few of them out here. All right? So let's do that. Yeah,
If you touch it, does the lightning go to your fingers?
Sorry?
If you touch it, does the lightning like go to your fingers? Yeah.
It's supposed to, right? Yes, as far as I know, yeah. Yeah, feel free to touch it. I don't know. What are the rules? But let's talk about doing some of these swaps in real life, right? So, we just want sort of any 5 people to come up and sit in these chairs. So 5 people, raise your hands. All right. Why don't you guys come up? The 3 of you in the front row? Yes, so, yeah. Come on.
Ungefär dubbelt så många medel.
1, 2, 3, 4, 5.
Du har 1.
So you're going to be 2. You be 3. You be 4. You be 5. All right.
Am I allowed to touch it?
You're allowed to touch it, yes.
I want one. You can have this for really cheap, you know?
Can you really?
Yeah, you can.
Yeah, that's the thing. Hang this around your neck so that we're essentially telling people that. So okay, so this is the situation that we begin with. Yeah. So 1, 2, 3, 4, 5. These are the 5 people who are about to like swap minds or whatever. And right now, 1, 2, 3, 4, 5. Can you quickly say your names? Justice. Alexandra.
Sophia?
Rasmus.
Sophia. Yeah, and then
Rasmus.
Rasmus, right. So right now, each person is in their correct. Each person's mind is in their correct body, because one is under 1, 2 is under 2, 3 is under 3, 4 is under 4, and 5 is under 5. All right. Now, what I want you to do is, let's say, starting with Justice, stand up and choose and come sit down here, And you can just choose anybody out here among these 4 people to sort of swap minds with. So essentially what I want you to do is, you're going to sit down out here.
Yeah. Fine.
Somebody else is going to, keep this around your neck.
Keep this around.
Keep this around your neck. And somebody else is going to come sit next to him. And then once you're sat down, all I want you to do is to exchange cards. Okay? To exchange the cards around your neck. So we're going to do this in a way that, so you choose anybody, then that person will come down and choose anybody except Justice, because we can't swap with him again, and so on, and we'll do it for about, we'll do this 6 or 7 times. All right, so just choose anybody out here, choose 5. Okay, so 5 is going to come sit. Their minds are going to swap cards. So now Justice's mind is in Rasmus's body, and Rasmus's mind is in Justice's body. And now you can go back to your seats. Yeah. Now, yes, go back to your seat. Now, any next pair of people come up as long as you're not 1 and 5. So, why don't you come up and choose somebody else, but don't choose. I mean, you haven't swapped before, so you can choose anybody. So.
4.
Right. So you were 2 and 4. So 2 and 4 swap.
You don't have not
2 and 4 are swapped. Yes. So now, yeah, go back to your chairs. So now, any other pair can come back. So just as you want, you can also come back. So somebody who's participated can participate again, as long as you ensure that the person you're swapping with, you haven't swapped with before. So why don't you come back? No, sorry. Yeah, number 3.
Number 3.
Yes, one time. And switch with anybody else. Choose anybody else to switch with. Hold on. One is 1 second. By 1, we mean the actual person 1. So we mean, we refer them by their name. So, or by their number. So, right.
Jag måste hålla. Vi kan göra något.
Yeah, have a seat. All right. If you swap, yes, come back up.
5.
No.
Yes. Sorry, what are the numbers?
I was 2.
You were 2 and you were 5. Yeah. So 4 swaps have taken place. We can keep going until we reach about 8 or 9, because after that they're going to start overlapping. So another way, Sophia? Yeah, go ahead. That's it. Let's do. Real mind swapping is happening. All right. Have a seat. Have a seat.
Mind swapping.
Yes. Come back up and somebody who you haven't swapped with before.
1.
1. All right. All right. And how about 1 is right. So now Justin has been accidentally returned to his own mind, which is fine. But let's try and correct that. And Justice, sorry, come back up. Sorry, Justice,
4.
come back up. Sit down, and somebody else swaps so that they don't have. Yeah, correct. So it's actually swapped. Well, so 1 and 4, right? All right. So if everybody's convinced now that they feel like they swapped enough, we've had 7 swaps. So maybe let's stop there. All right. Let's stop there, and we're going to do 2 things. First of all, don't move from your chairs. We're going to first, well, we can see that this is a permutation, right? 1 is going to 5, 2 is in 4, 3 goes to 2, 4 goes to 1, 5 goes to 4, which is to say that Rasmus's mind is in Justice's body, and well, 3 is well, 3's mind is in. It's confusing to me also. Well, yes, 3's mind is in 2's body, and so on. So, all right. So first of all, this is the permutation. In 1-line notation, the permutation that has taken place. We're going to call it. Let's call it pi for pi day. Okay. Yes.
Yeah, I don't think I swapped back to 1 now, and I've swapped with 4 people here.
You swapped with 4 people, so exactly. So we're going to stop now. So you can't participate in any more swaps, and we're in fact stopping the swapping process. So now we're going to say that these are all the mind swaps that have occurred, and what we want to do is now represent sort of unswap you in a way that you don't use any of the swaps to undo yourselves. So essentially, you're going to use Eileen and I as helpers, and we are going to have the names, x, x and y, and we are going to take turns for swapping with each of us to return yourselves to your correct, return each mind to the correct body. All right. But good point. Yes, that's a good point. So you've already swapped with 4 people. So no matter who you choose, you're going to repeat, and we can't have that. Good. So let's talk about this permutation that we have. Well, we have 5, 3, 2, 1, 4. That's 5, 2, 1, 4. We're going to name this permutation pi for pi. So what is this permutation in terms of cycles? Maybe somebody else in the audience can help me. Who hasn't participated before? Anybody? Any takers? I want to represent this in cycle notation. I want to represent this as, where does 1 go? What happens to 1? 1 is being mapped to 5 out here, right? Because 1 is in 5's position. Then what happens to 5? 5 goes to 4. So we have 1 in position 5, 5 going to 4. What happens to 4? 4 goes back to 1. Perfect. And similarly, you can see 2 and 3 swap places. So that we have the permutation that we have consists of 2 cycles, and they are 1, 5, 4 and 2, 3. Now, let's handle the case of 1, 5, 4 first. So persons 2 and 3, can you sit up? Can you get up and maybe sit in the first 2 seats?
Yes.
We're going to come to you in a while, but what we have to do, the way we sort of undo these swaps, is to take each cycle and use Eileen and I to perform a series of swaps on members of the elements in each cycle, and then we will return. We'll start by returning 5, 1, 4. 5 goes to 5's mind, 1 goes to 1's mind, 4 goes to 4's, right? So let's do that. So we're gonna take a moment now to just make this slightly more easier to read. So why don't the 3 of you sit in the middle 3 chairs? So 5, 1, 4 out like that. We don't have to do anything with this, but we are going to change these numbers out here. And we're going to essentially have, let's see, yeah, sit out here. So you have
4.
you were 4, yes. So we'll have 1, 4. Is this above you? And you were All right. Thanks a lot for your participation. Have a seat. And
You want your presentation back?
yeah.
well. And thank you, Arman.
Thanks
This
a lot.
was very nice.
Appreciate the opportunity.
Ja, nu pratar jag med er som ska vidare till nästa aktivitet som då börjar lite tidigare, för jag förstod att ni hade ett prov på fredag. Så ungefär 15:15 så börjar vi igen med nya aktiviteter och då ska ni vara i lite olika grupper, eller hur? Vi kan stänga av sändningen nu också, Kristoffer, om du inte redan har gjort det. Yes. Har vi de grupperna någorlunda klara?
Jag kanske får säga några saker.
Absolut, självklart.